Welcome YouTube to this video of radiation learning journal, radiation heat transfer. We are going to talk about Legendre polynomials this video. Now, before I continue, just want to quickly go into the solutions of the last video. Okay, so remember we can actually express in terms of sines and cosines, and remember the term inside is the same, the index inside is the same, and or you can express in terms of imaginary exponentials. Either way is fine, so do not get too confused. And yeah, the other thing is that we want to know what kind of values m can take. Is it integer values or any kind of values here? So generally, to solve your differential equations, you need some kind of boundary condition. And since this thing is talking about azimuthal angles, all right. Okay, so let me bring up GIMP. I'm not using Microsoft anymore, so I'll just use GIMP in place of Paint. So remember, in your azimuthal angles, you have an angle going from 0 all the way down to 2 pi, right? You have an angle going from 0 to 2 pi, all right? So from 0 to 2 pi, all right? From 0 to 2 pi, we have this kind of a situation, right? So if you have a sine wave, what are you supposed to expect? Well, you have to expect that the value, let's say, let me give this a different color. Okay, I'll use this color. Your value here, okay, if you have, let's say, phi of x equals to sine x, right? Sine x. So the phi at 2 pi, right? The phi at 2 pi should be equals to phi, all right? Phi at 0, right? And the other thing is that maybe you consider that the gradient there is the same. Phi prime at 2 pi equals to phi prime at 0. And these are known as periodic BCs. Periodic boundary conditions. So with periodic boundary conditions, the idea is that you can only have integer values, right? To satisfy this condition here and these two conditions here. Let me pick another color again. Cyan. Okay. So to satisfy this condition, for this equation, and you have these two conditions to satisfy, you have to make sure, because of periodic boundary conditions, that you have to have integer values of m, where m is over here. So if m equals to 1, you have something like this. M equals to 2, then you have something else different. You have to have a continuous kind of wave, so to speak. I'm not drawing it to scale, and of course the drawing sucks. This point should be here if m equals to 2. But you get the idea, all right? If it's anything but an integer, these two periodic boundary conditions cannot be satisfied. So to get the periodicity right, you have to make sure that m is an integer, all right? So m has to be an integer here. So that's just for reference when it comes to solving things later. Okay, m is an integer, please remember that. And okay, so let's try to solve the polar angle equation. So now we're going to talk about Legendre polynomials. Alright, so basically we have this Legendre polynomial to solve for Legendre's differential equation. But yeah, so this is the equation that describes the polar angle equation. And what does Legendre's ODE look like? It will look something like this, all right? So d by dx of 1 minus x squared dy dx plus L times L plus 1 minus m squared over 1 minus x squared, y equals to 0. Now in Legendre's ODE, L and m here, they are not necessarily integers, but as we found out just now, m for us, it has to be an integer in order to satisfy the periodic boundary conditions. Okay, so it has to be an integer for us. So that's one part of it. The other part of it is that, hey, look at this equation here. It does not look anything like this equation over here. So how are we supposed to make this equation start looking something like this? Or something like this. This is what you will get if you expand out the this equation here on the left hand side. So if you expand out this equation here, you will get 1 minus x squared d2y dx squared minus 2x dy dx plus blah 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 blah. Of course, anyway, for those who are watching, if you already know Legendre's polynomials, you can just skip a few videos ahead. You don't need to watch this video. Okay, you can carry on to look at how other spherical harmonics equations are derived. But if you are not familiar, do carry on watching. You're welcome to. So let's see whether we can convert our equation like this into something that looks like this. And for this equation, this Legendre's polynomial, the solving procedure is quite well, if you study a lot of ODEs, it's straightforward. You assume that y is an infinite series, and then you plug it in, and you see what kind of equation you get when you solve it. Alright, but for now but if you're not familiar with that, it can be a bit complicated. But hopefully, we'll get it. We'll tackle it when we get there. So first order of business is to convert this equation into something that looks a lot more friendly and looks a lot more like Legendre's ODE. Okay, so the solutions to Legendre's ODEs are known as Legendre polynomials, or one class of solutions are known as Legendre polynomials. More of that later. But this is very important part of what spherical harmonics actually looks like. So we need to know Legendre polynomials. So let's convert this equation into the Legendre type equation. So we can expand out the derivative that we see over here, this very messy d theta derivative here. So what we have on the right hand side, that is the derivative we want to expand out. So we use the product rule here. The usual, we will differentiate this term here on the right hand side into here, and then we'll keep the sine theta constant, and likewise we differentiate sine theta to give cosine theta, and we have the term over here being constant. So after you tidy all of this up, this is what your term will start looking like. So let's substitute this back into this equation on the right hand side, and you will get an equation looking like this. Alright, what then next? Okay, what is next? We'll try to get rid of some we'll try to tidy up our equation again. So we notice over here in Legendre's polynomial, we have L and L plus 1 standing by itself, and m squared is divided by something. It is actually divided by 1 minus x squared. So we'll try to get the basic idea is this: m over here in this equation will correspond to this m over here, and you'll have a few other dy's and dx, and then you'll have k as well, this k1, and k1 hopefully we can get it to equate to this L plus 1 thing over here. So that's the basic idea. So let's try to get k1 by itself. Alright, so we divide throughout by sine squared theta. Alright, and we'll get this equation here. We divide throughout by sine squared theta, so this thing disappears. This thing divided by sine theta. Here we'll have a cosine theta over sine theta, which is cotangent of some sort. Okay, so even after this, we still don't really have a Legendre looking like ODE here. So here's the magic we gotta do. That's not exactly magic, it's just a substitution of variables. We'll need to make the substitution x equals to cosine theta. Alright, so we know that there's the dy dx here, which is what we are trying to do. So we make the substitution x equals to cosine theta, and we'll need to do some substitutions in our ODE over here, just to make it look similar. So x equals cosine theta, dx d theta equals to minus sine theta. So by doing so, we can substitute d theta equals to dx over sine theta. So let's start replacing things term by term. So first we can do the simple ones. M square over sine square theta. We can replace the sine square theta there by sine square theta equals 1 minus cosine square theta. And that just reduces to 1 minus x squared, because x is cosine theta. So we'll deal with this term, and already you see it starts looking like the Legendre ODE, because it has a 1 minus x squared term at the bottom. So that's part 1. So after that, then we'll need to start dealing with these other terms one by one. Okay, so I'm going to deal with this term over here first, because that looks to be the most concerning, of course. So let's deal with this term and make substitutions bit by bit. So d2 big theta d theta square is actually equals to d by d theta. I mean, it's just the second derivative stuff. And now that we have this, we want to so-called get rid of theta as far as possible. So we make this substitution, d theta equals to minus dx over sine theta. So sine theta will appear on top, dx will appear at the bottom. Same goes for this derivative inside. And then we just do product rule. So I'm going to just skip the parts. Hopefully, I mean, you can take a slower look later. But basically, we just do a product rule on this one. And we get sine theta on the outside. Then we have this sine theta and the product rule of it. Long and short of it, you have sine square theta, d2 by dx squared, this big theta x, sine theta, d theta dx, d sine theta dx. So now, the thing is, now we need to differentiate d sine theta by dx. So how can we differentiate this? So, well, we know that x equals to cosine theta, and dx d theta equals to minus sine theta. So we're going to do some sort of a chain rule thing here, just to make life easier for ourselves. So we can do a d sine theta dx equals to d sine theta d theta dx. So we'll just substitute in as per normal. D theta dx is actually taken from here, 1 minus 1 over sine theta, and then you have this d sine theta d theta, which is just cosine theta. Then we'll have this minus cosine theta over sine theta, which is the cotangent, but I'm not going to do too much, worry about that too much. So when we substitute this expression back in, a lot of things start to cancel out. For example, let's see. This d sine theta d theta. So this cosine theta will appear here, sine theta will appear here, and the sine thetas actually cancel out. Okay, so as you can see here, I'm just substituting this equation with this in the brackets, and cosine theta appears here. So very nice, very neat. Okay, so let's convert all of this back in terms of x, so it's easier for us. As we know, sine square theta equals to 1 minus x squared. Cosine theta is just x. So all of this has now been transformed into something that looks like x. And for this final term, this other term here, okay, this term over here, d theta big theta by d theta, we're also going to do the same thing. So we're going to get rid of some of the more complicated terms. So we already know that from our previous differentiation, okay, from our previous differentiation, minus sine theta d theta x dx equals to d theta big theta d theta. How did we know that? Okay, so if you scroll back here, we see this, right? d2 big theta d theta square equals to this, and then we just substitute the derivative in. So this is like partially substituted. Okay, d by d theta of the big theta is equals to minus sine theta d by dx of this big theta. So we see that this d theta d by d theta big theta equals to whatever this term is here. So that's where our start point is. We can start from there. Alright. And then after that we are going to carry on. So look at this. Cosine theta, sine theta, big theta. Okay, so this is the fraction here, which we get from this expression over here. So we just substitute in the term for the big theta d theta, the capital theta thingy. Alright. Where is it? Yes, here. So we just substitute in this term, and what we get is d by dx of theta x, and then sine theta pops up to the front. And that's very convenient for us because again sine theta will cancel with this here. Alright. Sine theta will cancel with this here, and yeah, sine theta will cancel with that, so no problem. Where is it? Okay, yeah, anyways, sine theta will cancel out, and then you just have x on top, this theta, and d theta x dx. Actually, yeah, this theta function, you can actually just put it in terms of x. Doesn't really change anything, because theta is this unknown function that we are trying to solve. It can be in terms of theta, it can be in terms of x. Doesn't really matter, it's just a notation thing. Okay, so we substitute this expression back in here, and of course the first term, this first term we substitute as these two terms here, and by doing so we will get something like this. Alright, you get something like this, and okay, so we substitute the term on the right, and then we're also going to substitute this term over here with whatever we have solved earlier. We already solved for the second derivative earlier. Okay, so we're just going to copy and paste all of this inside here. Alright, after you do that, you realize that you start to realize that okay, I thought something looked a bit suspicious. Okay, I think that was a careless mistake again. I actually substituted this whole thing in here. I forgot to actually divide throughout by this big theta. Okay, so I had to divide throughout here. Okay, so yeah, and that was a careless mistake which I have to rectify because I did not paste this thing down. I only substituted this bit here. I forgot to divide throughout by this big theta of theta. So this 1 minus x should have a denominator of this big theta, and so does this x. So I'll have to make some corrections, but I'm kind of running out of time and I don't want the video to be too long. But thanks for watching. I'll see you guys again. So I'll continue the discussion next time. See you.